exponential growth as opposed to linear growth. And we will see that exponential growth is much quicker than linear growth. Many of us have already heard the term exponential growth, and it's always used in a almost growth out of control context. And we will see that this is a very correct way to look at things, or at exponential growth, I mean. So let's go ahead and start this. So exponential growth. This will lead into us discussing the exponential function, but exponential growth, basically it's anything that's growing exponentially. That is, anything that's got, some base. We're going to start off with 2, because 2 is kind of the easiest one to envision, but, this base can be anything. So exponential growth, we're going to be looking at this function right there, 2 raised to the x. So let's look at what happens. So if we have, x and then 2 to the x, we're only going to be looking at some of the natural numbers right now just because it's easier, but note that this discussion does extend into all the real numbers. So let's get into it. Exponential growth. So if we have 0, that's 2 raised to the 0th power. I know 0 is not a natural number, but it's fine. That's going to be 1, right? Anything raised to the 0th power other than 0 itself is going to be 1. Important side note, 0 raised to the 0 is undefined. Okay, so if when x is 1, we've got 2 to the 1st power. That's 2 times nothing, 2. Second one, we got 2 squared. Well, that's 2 times 2, so we got 4. And then we got the next one, that's 3. That's 2 cubed. What's 2 times 2 times 2? Well, note that this is just 2 squared times 2, right? It's double what the previous guy was, so it's going to be 8. And if I go to 4, well, that's going to be 2 raised to the 4th, double what this guy is, 16. And so when I go to 5, that's 2 to the 5th, double what this guy is, so it'll be 32, so on and so forth. So you get the idea. Now, what if this were just a simple linear growth situation? Well, linear growth, that's just 2 times x. 2 times 0 is 0. 2 times 1 is 2. And then, like it is over here. Let me go ahead and add some lines here so I can kind of read across better. All right, and then next one we're adding 2 each time instead of multiplying by 2. That's the big difference here. So add 2, add 2, add 2. So note that the growth here starts off pretty in line with each other, even up to this point, but then begins to diverge at this point, and then over here, note that there's a huge difference. So there's a big difference between linear growth and exponential growth. And when you look at the graphs of exponential versus linear, you can kind of really see it demonstrated. Here's a typical linear growth pattern. You can predict that pretty easily. That's the linear growth. It's just a straight line. Human mind can see a straight line very easy. Human mind has great difficulty comprehending exponential growth. I've looked at the equation quite a bit, and even I sometimes have my mind boggled and blown. But exponential growth goes like this, and it shoots up. And note that the rate of increase is itself increasing. That's what makes exponential growth so fast, so hard to keep the human mind wrapped around. There's an old quote that says that there's only two types of people that like exponential growth, and those are the mentally insane and economists. And it's simply because of the out-of-control nature of it. And typically, because it gets out of control, anything that you're modeling with an exponential function does eventually break down before it gets too far out of control. So let's look at an example here. I want you to take a sheet of paper, pull out a sheet of paper, and I want you to fold. Look at the thickness of this paper. We're going to be folding this paper in half, right? And of course, we're going to be taking this to a ridiculous place, but for right now, we'll stick with normal sheet of paper. If you fold it, that's 2 thicknesses of paper. You fold it again, you have 4 thicknesses of paper. So we're going to start off with this thickness of paper. It's about 1/2 of a millimeter thick is what number we're going to use. And we'll be looking at it on this graph. All right, so we've got the first thickness right here. We got it at we estimated it at about 0.0001 meters, and that's if you do 0 folds. All right, and I said half of a millimeter thick. I guess that's a tenth of a millimeter, but it's fine. So that's if you don't fold it. We're right here, and if you do fold it, then you're double, right? You're 2/10 of a millimeter thick, and so so you know what the scale is right here on the X scale. You've got the number of folds going along here, and then you look over here. This is the thickness of the paper. So you fold it over. This is what would happen if you stack 2 sheets of paper. Let's go ahead and look at it. All right. So you've got your paper like this. It's just sitting here. That's what happens when we're here. You fold it once, you get to here, 2/10 of a meter. Fold it again. That's 4 sheets of paper. You've got 4/10 of a meter. All right. So far, so good. Fold it again, and you get 8/10 of a meter. That's this equivalent of 8 sheets of paper. Fold it again, and you'll have the equivalent of 16 sheets of paper right here. So note like how the rate of change in between two is growing as we go up and up, right? So right here, the distance from here to here, note from here to there is the same as the distance from here to here. And then the distance from here to the bottom is the same as the distance from here to the point, right? We're doubling. All right, and then we fold it again. You note how these differences are starting to seem less as we move on up the scale. So we're all the way up to here. We fold it again. That brings us to here. Fold it. Take your paper. Fold it one more time. And now you're at the thickness of a human hand. This is probably the last fold you'll be able to actually physically do with your piece of paper. From here on out, it's going to be hypothetical. But note that just after how many folds is that? That's going to be 7 folds. We're at the thickness of a human hand. Now, only 7 folds to get us there. Now, if you wanted to stack sheets of paper on top of each other, that would be linear growth. You would have to stack 128 sheets of paper to get the width of a human hand. But we're able to get to that with only 7 folds of a sheet of paper. So you can kind of see how much more quickly exponential growth is. And this is just with a base of 2. Now let's keep going, because if we fold it again, it took us 7 folds to get to the thickness of a human hand. We only need 1 more to get twice that of a human hand. If you look at the paper, you can kind of see how it's going to be definitely double. Just kind of look at the paper you folded and then double that, and you can see that's definitely thicker than your human hand. All right, so that brings us up to here. And so we fold it again, 4 times the thickness of a human hand, which just so happens to be the width of a human hand. Kind of like look at, doubling the width of your human hand, and then doubling again, and you can see you definitely will get the thickness of the human hand. Now this is only after 9 folds of a sheet of paper. So yeah, again, 9 folds. That would be 512 sheets of paper stacked on top. So you'd have to get to the 512th iteration for linear growth to get to where you're at with only 9 folds. All right, so you fold it again, and now you're at twice the human thickness, so that's after 8 folds. Just put it right on top of each other like that. All right, sorry, I pressed the wrong button. Here we are, human hand width of 9 folds. So if we do 1 more, then we're going to be twice the human width, putting us right there. And then if we fold it again. And so note how quickly we're increasing, right? Getting up to the thickness of a human hand seemed pretty incredible. But note at this scale how quickly that's becoming a kind of a meaningless milestone, because now we're way up here. And so if we do it again, that's going to be increased even more, right? Human hand width, human thickness at this scale is starting to seem less and less of a difference. And now we're up here at a desk height, and this is only after, 13 folds. 13 folds gets us the desk of a height. you would have to stack 8,192 sheets of paper to get up to the desk, a desk height. So that's, for a point of reference, linear versus exponential growth. We fold this paper over again, we're going to be double the desk height. And so now here we are at 14 folds. We're about at the height of a human, right? Stand up straight, stick your hand out. That's how high we are after only 14 folds of the paper. Pretty incredible. All right, so let's fold it again. That puts us up there. Sorry, that puts us up there. Right above 3 meters, and then we fold it one more time. Right, so at this height, or at this number of folds, this is 16 folds. You know, we are now 4 times the height of a human. And now here we are at the 17th fold. We're at the height, about the height of a typical 4-story building. Notice how all getting up to here, which seemed kind of incredible for folding a sheet of paper, is now seemingly becoming less and less meaningful. So as we keep going higher, you know, the next fold will be the height of an 8-story building, of course. Right there, and then we fold again. Yeah, and so note these are becoming even less and less. These distances are seeming more and more just closer and closer to 0 at this scale, and so we fold again. And now we finally reach the minimum height of a skyscraper. Fold it again. Right? Double the minimum height of a skyscraper. Fold it again. And now we're way up here. Note this minimum height of a skyscraper is seeming less and less impressive at this scale. Certainly all these other milestones are becoming less and less impactful. And now we're here at the height for the tallest skyscraper ever constructed. That is only after a mere 23 folds. All right. So now, after 24 folds, we are at double the height of the tallest skyscraper ever built. 24 folds, folks. Not a whole lot of folds. That'd be a lot of sheets of paper if we were stacking it end on end. And now at 25 folds, we are at 4 times the height of the tallest skyscraper ever built. All right. Now we're up here. Higher still. Notice that this tallest skyscraper is getting left in the dust at only 27 folds. All right, we get to our next fold here. At 28 folds, tallest skyscraper is starting to look indistinguishable from all these other ones, even the width of a human hand at this scale. It's not that much more on this scale. So all these things down here, note they're starting to become even more indistinguishable. All right, still going up. So we can see at this scale, all these things are starting to look more and more the same as we keep going higher and higher. And so here you see, after a mere 32 folds, we are now at the top of the atmosphere. Quite a feat indeed to only get there off of 32 folds. And if you want to know how many sheets of paper you would have to stack to get to that, just say 2 raised to the 32nd power, and that will be how many sheets you need. And so you can see now we're twice the height from the surface to the top of the atmosphere. Top of the atmosphere is here, surface of the Earth is here. This is where we're at. We're way out in space right now. Now we're 4 times the distance from the surface to the atmosphere, all by folding paper, and that's at 34 folds. Okay, you see where all these, even the top of the atmosphere, which seemed huge at first, is now starting to get left back here with everything else. Lower still. Right? Look how close that is to the bottom with everything else. This is how quickly exponential growth goes. Right there. Now look at this at the 40th fold, top of the atmosphere. It just barely even registers. And now here we are at the 43rd fold. We're at the average lunar orbit. It only took us 42 folds of a sheet of paper. Look how quickly all these things seem to be left in the dust. Also going to note how thin the atmosphere is compared to the distance from Earth to the moon. Very, very huge indeed. Now, how many paper would you have to fold to get to this point? Well, you just take 2, raise it to the 43rd power, which is about 8.7 trillion sheets of paper stacked on top of each other to get to the moon, or just 43 folds. This is the power of exponential growth. It gets crazy really, really fast.